abstract syntax. And then from there, let me do some operational semantics. Okay, and you'll see that everything goes smoothly now that you kind of understood where I'm coming from, where is this all coming. And by the way, lettuce to Scala is going to be very, very close. In fact, one of your assignments next week or somewhere would be to translate these lettuce programs directly into Scala expressions. And you will see how close this let binding is in Scala. It's just, there. Okay. It also happens in JavaScript. There's something called let, right? So you can do let bindings in JavaScript as well. Okay. Good so far? All right. So let me go ahead and do abstract syntax. So what is abstract syntax? Remember, everything in this language is now just an expression. So I just need to start about what could be expressions. And you could say an expression is a constant double. This is all from last week. So you're going to cut and paste all the arithmetic rules. It's an identifier with a string in it. It's going to be plus of 2 expressions. You saw all of this. And hopefully you're working on the differentiation part, minus of 2 expressions. So you have all of your arithmetic here. Okay, I'm just going to write plus and minus. Var versus val in Scala, is it similar to var versus let in JavaScript? Yes, absolutely. Same thing. Okay. You don't have the in part in JavaScript, but it's the same thing. I mean, the more you stare at languages, you see all these similarities, right? And that's great. Yeah, good. So you have plus, minus, identifier, all of that. Okay, so this is all the arithmetic part. I'm not going to bother with everything. I'll just put in some arithmetic to show you there is arithmetic here. Okay, and now I'm going to do a pastiche. And this is where I'm going to start to differ from what I did before. I'm also going to slip all my Booleans in here. So I'm going to say the greater than equal to of 2 expressions is an expression. The less than equal to of 2 expressions is an expression. The comparison of 2 expressions is an expression. The and of 2 expressions. Now you may be wondering, where am I going with this? The and of 2 expressions is an expression. The or of 2 expressions is an expression. The not of an expression, the logical not of an expression is an expression. Then you say, if then else of an expression is an expression. So if expression, so then you don't have to, in abstract syntax, you don't need to write if then else like that. So you write if then else like this. If then else has 3 arguments, all of which are expressions. So this is written as, suppose the first argument is, let's call it E sub 1. The second argument, let's call it E sub 2. The third argument, let's call it E sub 3. In concrete syntax, this is if E1, then E2, else E3. I'm just packing it into one abstract definition in the grammar. Hopefully you have seen all of this, right? But it's not appearing in the way you would have expected it to appear. And then comes the last but not least, which is the feather in the cap, which is our let binding. And our let binding in the abstract world looks like this. So you have let, you have a string, which is going to be, I'm not going to use identifier, but if I were using it, it would be an identifier. And then you have 2 expressions. The first expression, let's call it E1, let's call it E2. And this abstract syntax stands for let, let's call this ID, identifier. ID equals E1 in E2. So this little bit of concrete syntax, in the abstract world, you extract the bits of information you need, the identifier that goes into the string, the first expression on the right-hand side of the equality that goes into first argument, second argument, and then this goes into the third argument. This is the grammar. And it's not what you would have expected. This grammar looks like my morning smoothie. Whereas if you had looked at something like the Mython grammar I wrote before, that looked like a nice salad. You would be served with all the ingredients. It's what you would call a deconstructed salad. Okay. where all the different ingredients come together and you are supposed to mix it. This looks like, I don't know, the morning smoothie where I put all the stuff in. I look into my fridge and I see, okay, here's some here's some eggplant and whatever stuff I wouldn't eat normally. Cook, I would just put it in there, blend it all, put some sugar, maple syrup, and some protein, and I drink it, and that's supposed to keep me healthy, right? This is exactly the same thing. I've taken arithmetic, I've taken booleans, I've taken if then else, and I've taken let, and I've put all of them into this one big grammar where there's just one non-terminal called expr, and everything is there. That good? So there is a problem here. This allows me to write nonsense. So as an example, you would not have let me write a program like this. You would have said, let's do 1 greater than equal to 0 minus 25 plus sine of x greater than equal to 45 plus 222. You'd be going like, this is complete nonsense. But this kind of a program can be written in my abstract syntax. Why is that? This part is just GEQ. This part is just GEQ, const 1, const 0. Okay, let's call this E1, this part. Okay, now this part is some other expression. Let's convert it to abstract syntax and call it E2. And the whole thing is like minus of E1, which is this part, comma E2, which is this whole mess converted to abstract syntax, right? So now I'm taking something that's true, false, and from it I'm subtracting something that's a sum of a number, the sign of a Boolean condition plus a number. What does this all mean, right? So it depends, right? So these expressions are meaningless, but I allow them in my syntax. So there is this thing about syntax error versus type error. So in my lattice, these kinds of expressions are just allowed. I've just made this big mess of all kinds of expressions. So these are allowed. The only thing I'm not going to worry about right now is whether this makes sense or not. I will allow you to write them. But when I'm going to interpret them, when I'm going to evaluate them, I'm going to stop and say, hey, you have something that's a Boolean and from which you're subtracting something else. Or when I get to this part, I would say, hey, you're trying to add a Boolean to 222 and I don't allow that, right? So there is this thing where I allow this in my syntax, and you would be like, why? But I just do. And that's a choice I made. It's a design choice. And that keeps my grammar really, really, really simple. But I have to catch it at some point, and I'll catch it when I'm going to try and execute these programs. So it's a design choice I made. Whereas in my previous attempt in Python, how would I have done this? I would have done different non-terminals, right? So I would have called these con dxpr. And for this, I would have tried to call it a statement, right? But remember, in functional programming, we don't do those kinds of hierarchies. We think of expressions all the way from the program is an expression that's made up of expressions, which are made up of expressions, which are made up of expressions, Like in some cultures, they think the universe is made of tortoises that are standing on tortoises, on top of tortoises, on top of tortoises. And then you would say, what's underneath it all? And you know what they would say? A tortoise. Okay. So you really have this this whole thing that expressions are expressions, which are made up of expressions, which are made up of expressions, in turn made up of expressions. And that's how we are going to go with this whole route, okay? All the way down to constants or variables or whatever. Is everyone okay with this? If you're okay with this, let's try and write some meaningful examples, not meaningless examples. So let's do let x equals 10 in x plus 5, as simple as it gets. Let's try and write this in abstract syntax. What does such a program look like in abstract syntax? This is concrete, human friendly. What does it look like in our abstract world? So go back to the grammar. Remember, there's a let with 3 things in it. string, expression, expression. So this better be that. So this better be a let with a capital L. It better have three parts: a string, an expression, and an expression. So tell me, what are the three, what is a string argument to this? What's the identifier argument to this? The string X, very good. Often I won't put the quotes around X, but I'll try and be as formal as I can, but I'll slip up. You know, uh, if you catch me, just let me know. Eventually you will be like, yeah, I know what he means, and I know what I mean, and all that. So let's just live and let live at that point. But now just catch me, okay, so that I know you understand. All right. Now, what is the first argument? How do you write 10? Very good. You write it as constant. So you wrap it around a const and you say constant. In abstract syntax, you wrap everything around constructors if you can. Okay. And what about this? The last part? Very good. Someone got it. Laura got it. Plus ident of x const of phi. Okay. Now this whole thing is the program. Is there a particular reason we don't wrap? Very good. That's an excellent question, Kai. So Kai's question is this: why is this not wrapped around an identifier? Why didn't we do ident of x? Okay. Now let me ask the following: what kind of thing is ident of x? So look at this and say, what is ident of x? What kind of a beast is it? Is it an expression? Is it a string? Is it elephant? Like, what is ident of x? What's its type? Its type is an expression. Okay. So when you wrap a string around an identifier, it becomes an expression. Is that okay? So for example, when I put on like suit and tie and shining shoes and go out, I become like a rich person, like a gentleman, right? Okay, I need a walking stick and a large pipe, and then I can become a gentleman, right? So that's like me wrapped around in a suit. I become a gentleman. So that's exactly what you're doing to a string. You're making it an expression. Now look at the definition of let. The first argument needs to be a string, not an expression, not an expression, right? So you should not wrap it in an ident, because that makes your x into an expression. Oh, no, no, no. Gentlemen are not allowed into this club, right? This is for like people who know how to have a good time, right? Fine. So there you say, okay, you're not allowed to put in ident over x because that's not allowed. What you're expecting here is a string, and what you should be providing there is a string, not an expression. So types matter in this class a lot, okay? And I will keep, asking you, is it type checking? And that means that, is everything falling in the right place? And if you put an ident of x, it doesn't fall in the right place. It falls in the wrong place, okay? Another way of thinking about this is a very bad terminology in C++. It's called L value and R value. I hate that terminology because it's so unclear, but you can think of this X on the left-hand side as an L value and the one on the right-hand side as an R value. But I used to think that way when I was a student, and they exposed me to C++, and I was quite confused. What is this L value? Can you define an L value? The definitions I got were never satisfactory. So I'm never comfortable with this concept, but if you've seen this before, it's roughly what it is. One of them is the name that to which you're binding something or defining something. Here, when you say ident of x, this is a usage. This is declaring that I'm using the value of x. So whatever value you have in x, I want to use it here. Okay, so far? All right. So the abstract syntax allows some things which have slipped in. So it allows you to write things like this. So you can write x greater than equal to 10 and y greater than equal to 45. And this you do by saying and then you say GEQ ident of x, const of 10, GEQ, ident of y, const of 45. So you can write Boolean expressions. You can also write conditional expressions. You can say if this entire mess here, then x, else y. So you can write this as if then else, copy and paste this entire thing. Let's call this E. So put E here, this entire E here, and then you would have ident of x, the then branch expression, and then the else branch expression. So you can have if then else. Good so far? And you can have some strange things in this language. So this language allows you to write let x equals 10 in x plus 45, the whole thing, plus let y equals 15 in if y greater than equal to 45, then 15 else 23. So you have this expression E1 plus this expression E2. But E1 and E2 are themselves let bindings. Okay so far? So let me ask you a simple scope question. Is x in scope here, thereabouts, where you talk about 23? If I replace this 23 by x, is that allowed? No. Very good. Very good. Because x came in and out of scope in this red box that I'm drawing. I'm drawing too many red boxes today. Green box that I'm drawing. So in this green box, x came in and out of scope, no more. So x came in scope here and x came out of scope, went out of scope here, so no more x. So you can't have any more x being there. Okay, so there you go. Good. So now you understand everything that we can do in lattice. All right. So then let us talk about the semantics of these things. Oh, does it still become 55 plus 25? Yes, it does. I think I meant to do a 5 here, so 25. Yes, you're right. Absolutely right. Yes, let us talk about too many puns, huh? Thank you. That was unintentional though. All right, so let's go about doing this. Semantics. So it goes. All right, so let's start with this, okay? Semantics. Semantics, remember, is just defining this great function called eval. So eval has two things, an expression and an environment. Okay. All right. So what is an expression? Now the expression is going to be expanded, vastly expanded. So previously we had our little bit arithmetic here. That's what our expressions were, right? Now our expressions is our this entire mess of things are going to be expressions, and we want to eval everything that we can eval and tell you when something is broken that we can't eval. All right, that's the idea. So this now our expressions have expanded vastly in scope, and so we have given some semantics already. We've given semantics to const, ident, plus, minus. So we gave semantics to all of arithmetic last time. So we will keep those semantics and build on top of semantics to define semantics for conditional expressions. Let's start with that. Okay, and that should not involve any big problems. I will point out to one or two subtleties there. Semantics to if then else, and semantics to let binding. So those are the three things I'm super interested in getting to if I can. Okay, let me start with semantics for conditional expressions. So I said those are no big deal. So let's do that. So let's do semantics for greater than or equal to E1, greater than or equal to E2. My expectation here is that I can only compare numbers. But what is happening now is the value of this is going to be a new type called Booleans. And previously, the number of the types that I had were numbers and error. Error was a type. Okay, so now in my value, I allowed you to have a value called error, and I had all kinds of numbers, like all possible numbers there. Now I have to add to my value domain a new kind of variable called Boolean, which can be true or false. And numbers are represented by the set R. Error is just error. It's just one thing I'm going to call error. Boolean, I'm going to represent by the set B. I'm going to call it Boolean. So now my set of values is either an error or a real or a Boolean. Why is that? Because my programs can now produce Boolean. My expressions can now evaluate to things that are true, false. So I better make space for that. So I better add a new type called Boolean to my language, and I better get ready with Booleans. With all of that, then life becomes easy. So what's the semantics for greater than equal to? Very simple. So I say you are interested in evaluating an expression which is GEQ of two expressions, E1 and E2, under an environment E and B. What should you do upstairs? On the top of the line, you should say, let me evaluate E1 under the same environment, E and B, and let's say the value I get is B1. When does it make sense to proceed any further? What kind of value should V1 be? Can it be an error? Can it be a real, or can it be a Boolean, or all? Boolean? Think again. Can I compare Booleans in my language? Do you think, try this in Scala. Try to say if true greater than equal to 2, is this allowed? Try true greater than equal to false. Is that allowed? Try, I don't know. So it depends on your language design, right? It really depends on your language design. So maybe I want to compare true and the number 2. Maybe that's allowed, right? I think JavaScript allows this. Okay, JavaScript actually lets you do this. I think, but don't take my word for it. Just see whether that happens in JavaScript. Okay, I think some languages definitely allow you to do for this. C++ definitely allows you, right? Anything is allowed in C++ with the right typecasting. But let us just say numbers in our language. It makes sense to compare numbers, but Booleans, no, I draw the line there. So then I say V1 better be a real number. And then let's evaluate E2 under the environment. Let's call the result V2. And let's say V2 better be a real number. And these are important. It's important to say these because in my language design, I am only comparing this. Right, but yes, you're right, Logan, that in some languages, false and true naturally get converted to true 1 and 0 whenever you feel like it. And guess where you're going to deal with that semantics in your assignment. So I kid you not, I do have an assignment where I ask you to do exactly that. Allow letters to convert numbers into Booleans and so on. Some languages do, but let us say in the class version, we don't. We are a purist language and we don't do that. So then what's the answer? The answer is true if V1 greater than equal to V2, false otherwise. People will sometimes say this is too much notation. Just write it V1 greater than equal to V2. If that holds, then it's true. Otherwise, it's false. So that's the basic semantics for greater than equal to, and we'll call this OK. Now we have some error rules, and there are 2 error rules we have to consider. The first rule is this one. I want to eval greater than equal to E1, E2 under an environment. And when I eval E1 under the environment, I get a value which is not a number, which is not in real. I could have written this out like this. Same thing. Then this whole thing is an error. And this is GEQ, error rule number 1. Similarly, you have to write an error rule number 2. In error rule number 2, you would look at the case where V2 is not a real, and you have to write that rule as well. Good so far? And those 3 rules together tell you how to do greater than equal to, and that gives you a way to do it. And by the way, when I say v1 is not real, this allows v1 to be a Boolean, or it also captures the case where v1 is error, by the way. Both of the cases are getting captured, which is good. 2 cases, we are done. Okay. Everyone okay so far with the greater than equal to rule? Do I need to write a rule for less than equal to? No, right? It's basically the same thing, except you change this g greater than equal to symbol into the less than equal to symbol. Where are we so far? Good? Good place? All right, very good. So let's go to the next thing then. Let's do the semantics for something that's slightly more subtle. And this comes to the semantics. Let's do it for and I'll talk about something important that goes on with and. Okay. How do you do semantics for and? Well, the idea is the same thing, right? I want to evaluate the and of 2 expressions, E1 and E2, under an environment E and V. What do I do there? So I say, okay, let me evaluate E1 under the environment, and let's call that value V1. Now, what is the condition under which I should proceed for V1? What should V1 be to let me proceed with this evaluation? It must be a Boolean, okay? You cannot say 15 and 45 in lettuce. You can say that in C, C++ and JavaScript for sure. Okay, there is a conversion back from numbers to Booleans too. But I won't let you say that in lettuce. We are going to be typed, what are called strongly typed. So we are going to have very strong typing rules. And this is where they are getting inputs. So V1 is Boolean. In that case, let me eval E2 under the environment. And let's call that value V2. And V2 is also Boolean. And so I want to write this rule. It's just V1. And this is the logical land. V2. Okay, and I want to call this rule and okay. Very much along the lines of my greater than equal to okay rule upstairs, right? I just wrote this rule here. I just want to write the same thing for and. Anyone see a problem here? I would be very impressed if you do. There is a problem though. It's not actually a technical problem. It's just the way programming languages work. This is wrong. Programming languages do not do this. As a rule, programming languages will do the following. So to get an idea, try the following. Yes, Emma got this. Emma got this. Short circuit. Right. Programming languages do something weird. They short circuit. We already talked about a bad case of short circuiting for multiplication, like 2 lectures ago or something like that. But there is a good case where short circuiting happens, and that is for and. It does short circuit. And this is what happens in and. Try this in lettuce, or try this in Scala. Try this expression, 10 greater than equal to 35, and 0 divided by 0 equals 10 divided by 0. What do you think it's going to return? It's going to return false, not a division by 0 error. Okay? And the reason is programming languages short circuit. Programming languages short circuit. Why do they short circuit? Do you think you know what? Do you know why they short circuit? Is it because this is too much computation, right? Efficiency, right? As if like one extra little instruction here would make such a huge deal, right? So efficiency is not quite it. The reason you short circuit is, yes, exactly. So people in programmers got very much used to writing code in this pattern. And this is very much a C++ mentality that came through. So what people would do is, instead of saying if error condition, then do something else, right? So a lot of times you want to check an error before you do something. The most common case you do that is for pointers. In C++, you would say if star pointer ptr equals 10. So you want to check whether the contents of a pointer is 10. But let's say a pointer can be null. Exactly, right? So what you want to do, programmers are very used to doing this. So people would say if PTR and star PTR equals 10, okay? And what they're doing here is this. This PTR checks if a pointer is not null. Okay, and if you had a slightly more uh, you know a more professional programmer, they would wrap this around a function or a little macro that they would call is null, so that poor people like me who read their code can see this. But the point is, you would check whether a pointer is null. If it is not null, you proceed to do this, and this can be done safely now. If you did not have short circuiting, if C++ did not have short circuiting, do you think code like this will work safely? Nope, because you would check whether a pointer is null. You would take the in direction of the pointer and check whether that is 10. You would have both bits of information, then you would AND them. No, 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 that's not how it's done. What AND does is it checks whether the first condition is false. If it's already false, the whole thing is false. But if the first condition is true, then it goes on to check the second condition. So the reason it's done is not efficiency. The reason it's done is for this strange coding pattern that programmers, early programmers who programmed operating systems and stuff, just got used to writing code this way. And once they got used to writing code this way, when they moved to other languages, they expected other languages to have this semantics. So you have this check and do semantics, like check and check semantics, where you check some condition and then you go ahead and indirect a pointer or do something. Okay, and so that's why it's stuck. So we do short circuiting. So which means that this rule is not correct, or our OK rule is incorrect. So what we do is we do a short circuit rule. So what is short circuit rule? It goes like this. So let me go ahead and let's do a new rule. I have plenty of space, see? So let me do a new rule. So this is a short circuit rule. So you say eval, so let me write in the top. Eval E1 under the environment is false. Then eval and E1, E2 under an environment is false. This is and short circuit rule 1. And then you would say eval E1 under an environment is true. Eval E2 under the environment is V2, and V2 is a Boolean. Then you would say eval and E1, E2 under the environment is V2. Is that okay? So this is the two short circuit rules, right? And short circuit 2. So this is how programming languages do AND. What about OR? How do programming languages do OR? They short circuit as well, but they short circuit in the other direction. When do you short circuit OR? Yes, you short circuit OR if the first argument is already true, then you short circuit and just say the whole thing is true. This is dangerous, by the way. It's okay for simple patterns, but I have seen like major errors in software. Like once I was trying to, they said 20 years of operation and they hadn't seen any errors. So they challenged me when I was in the industry to find bugs, right? And I wrote this simple static analysis tool for C to find these errors. And sure enough, it found errors. They had, in many places, they had done stuff like this. So they would check a condition and they would do something else. And in the something else, they would have side effects. So they would call a function, they would do some arbitrary code in this something else. But then if you had short circuit, if this check failed, then nothing of this would happen, and that they didn't expect. So then I found lots and lots and lots of errors just by figuring out that because they had short circuited, things are not going to happen. Right? In C++, the worst things people do are like write assignment statements in here, I mean, it's supposed to be an if then else, but they write assignment statements, call functions, ask the rocket to fire the thrusters, and so on and so forth. Okay, this was a really good lecture, if a little bit slower than I would expect, but thank you everyone. I feel a little bit better already. If it were a real class, I would have gotten gummy bears the next time, but since it's not happening, I'll get you gummy bears when you meet me, hopefully when this is all over. I'm still not done with lead bindings. I will do that next lecture, and I will do a brief tour of if then else. I'll do that next lecture as well. So next lecture, we'll complete the little bit of things that we couldn't do today, go on from there. Thank you. Thank you so much.